Watch what happens when automated decisions hit an unverified network. A data pulse bypasses the barrier, enters a secondary loop, and compromises the entire system. When we analyze execution traces from multi-agent large language models, the data reveals a surprising reality. 44.2% of catastrophic system failures have nothing to do with bad prompts or malicious jailbreaks. These failures originate from flaws in the graph topology. Incorrect wiring causes agents to bounce data indefinitely until crashing. Orchestration frameworks attempt to prevent this by deploying runtime guardrails at the pipeline's end, trying to intercept harmful outputs only after they are generated. This approach creates a massive engineering paradox. We are using one stochastic, highly unpredictable model to catch the runtime errors of another. Relying on output filters completely ignores the structural integrity of the underlying pipeline. It treats the symptom while leaving the broken architecture intact. Treating a complex network of stateful agents as a simple linear prompt chain obscures the structural flaws that lead to systemic failure at scale. To fix this, we have to stop waiting for the system to break during execution. We need to implement verification at design time. In traditional software engineering, design time is the period before execution begins. A compiler checks the logic and proves the structure is sound before it ever compiles the code. Agentic systems require the exact same standard. The graph topology must be mathematically proven to be sound in advance. We have to map the connections to guarantee that unauthorized data leaks or runaway execution loops are structurally impossible. Moving from reactive prompt filtering to proactive architectural safety requires treating these models less like chatbots and more like complex engineered machinery. To achieve proactive safety, we replace linear prompt chains with rigorous agent-based modeling structures. We formalize the workflow using a strict parameter sequence. A verified system is defined by its agents, state variables, message types, behavioral blocks, execution edges, and guards. Execution edges dictate the operational dependencies during a single workflow step. These pathways must be strictly acyclic. They flow in one direction, without ever looping back on themselves. When an agent needs to remember an interaction or adjust its future behavior, it writes that update directly to a persistent state variable. This preserves the feedback safely in memory, rather than triggering an immediate operational response. Without this separation, developers accidentally build cyclic execution graphs. These unverified loops trigger race conditions, forcing agents into rapid-fire infinite back-and-forths. Decoupling acyclic execution edges from persistent state variables is the mandatory prerequisite for system stability. Let's apply these structural rules to a concrete example, an automated social media account moderation system. This diagram illustrates the necessary architecture. In the top section labeled Account Moderation, the expected flow moves sequentially. A post is observed, evidence is resolved, and a state manager decides whether to restrict the account. A common architectural injection error occurs when a developer directly connects a raw observation node to the final enforcement action, bypassing the resolution steps entirely. The immediate consequence is severe. An account gets banned based on an unverified raw signal, like a single user report, without any aggregate policy review. Our framework detects this using Rule 1. Ungrounded state changes are prohibited. Any action modifying an account's state must trace directly back to a node that interprets aggregated evidence. It also triggers Rule 4. Missing decision gates are prohibited. Strong actions like banning require a dedicated policy mediator to authorize the command. A design time compiler flags these topological violations instantly, long before the system processes a single piece of user data. A runtime guardrail fails here, because an LLM evaluator cannot fix a graph that inherently routes raw data to an execution trigger. The blueprint itself is the problem. The stakes elevate when automated governance systems possess the authority to permanently restrict users. Looking at the bottom section of this workflow diagram, labeled Edit War Due Process, we see an architecture designed to handle complex user disputes, charting the exact path from enforcement to the appeals block. Consider a scenario where the enforcement agent successfully determines a user violated a policy and bans their account. There is a hidden logic trap built into this flow. The enforcer strips the user of their write permissions across the platform. However, to submit a case to the appeals node, the user still needs write permissions. Verification Rules 11 and 12 mandate that escalation paths and procedural recourse must remain reachable, regardless of the enforcement state applied to the user. By stripping write permissions before an appeal can be filed, the system has generated a systemic deadlock. The user is trapped without a mechanical way to request review. Design time semantic constraints fix this before deployment. They translate the abstract legal concept of due process directly into verifiable graph parameters. Guaranteeing procedural safeguards is a mathematical routing problem, not a generative AI problem. These theoretical rule sets are now a functional prototype. This is the AI Security Designer, which actively maps and verifies control flows. Tested against 48 workflows with known flaws and 168 complex variants, the verifier successfully identified the exact node where the architecture failed. The verification prototype achieved 100% precision, 100% recall, and 0 mean absolute error. Even when developers attempt to mask structural errors by splitting tasks across redundant agents or merging intermediate steps, the verifier registers 0 false positives. Subjecting these networks to formal compilation demonstrates that agentic behaviors can be mapped and validated using the same structural rigors as traditional system design. As these systems mature, multi-agent networks will span entirely different organizations and proprietary platforms. This creates a new problem. Individual nodes will operate as opaque, third-party black boxes, shielding their internal state logic from outside observation. Mathematically verifying the topology of a distributed graph is difficult when no single entity owns the entire map. A locally safe agent can trigger a catastrophic loop if it connects blindly to an unverified external node. Establishing a shared registry of verified behavioral blocks offers a roadmap for connecting these independent systems without compromising architectural safety.